Good to go? Is it like streaming live and everything? Whoa. Surprise! Here we are. Well, thank you all for coming in for my talk today. Good to see so many familiar faces. And today I'm Jill. I'm going to be talking about batteries, and I'll get into who I am and why I'm qualified enough to talk about them, I guess I could say. But my talk's called Electrification Insights. And just a little bit about me. So I do live in Santa Barbara. I'm a local here, and I work as a battery technology consultant. I've been working in the battery industry for over the last decade now, and I have a few hobbies I have listed there, but feel free to reach out if you ever want to talk about batteries or you need battery support. Think of me as your local battery guru, I guess. But thank you all for coming too. So today we're going to talk about the battery value chain to start, kind of set the pace on what we're thinking of when we think about batteries. Then I'll get into what's a lithium-ion cell and talk through the trends. And I'd really love to hear from you guys what topics you'd like to hear about, because I feel like I could talk on a lot of different things, but I want to make this relevant for where your mind's at, because battery technology is definitely, you know, here right now. It's trending, you could say. So getting into the battery value chain, I have to say, so I was a physics major in college, and I had no idea what I wanted to do. I was just interested in science, and I took an electronics lab class, which I love the electronics lab we have here, like, right, all the oscilloscopes and everything. Love that class, and the professor invited me to do research in his lab on fuel cell technology. And when I was doing fuel cell research with him, I started learning about how we really need clean energy. That was my first introduction to like the energy crisis, as they would call it back then. And as I was doing more and more fuel cell research, I realized that there were a lot of barriers to the commercialization of fuel cells. And so like today we have so many electric vehicles, and some of them are fuel cell vehicles, but you'll see the majority of them use batteries, because batteries are lower cost, the supply chains are there and all of that. And so I realized in fuel cell research that I wanted to work on a technology that was closer to being commercialized. So that's why I shifted into battery technology. And batteries are being used more and more for a variety of different applications. The three major sectors are for like grid scale storage, so stationary energy storage. Then you have transportation, like electric vehicles, electric buses, electric trains. And consumer electronics and devices are basically a very saturated market. It's been around for a while. The markets that are really growing right now are mostly the electric vehicle industry, but also the stationary storage market. And when we think about the adoption of battery technology, we have to think about batteries in a form of circularity and looking at what we call the battery value chain. So batteries are personified a lot of times, right? If your battery dies when it runs out of power, we say that. If we're going to do an analysis of a battery and we open it up to look at the materials, we call that a post-mortem analysis. Batteries have a cycle life. They have a state of health. Like, we relate to batteries as a living thing almost. And when we think about the value chain of battery, we think of it as the life cycle of a battery. Just like we go through phases in our life, batteries go through phases in theirs. They start out raw materials, then it goes on to the metal refining, the cell production, battery manufacturing, and then they're integrated into a device like an electric vehicle, and they have their first life. And when their state of health is a bit decayed, they can be moved potentially, hopefully, into a second life or even third life before they're collected and recycled. And then those recycled battery materials can flow back into lithium-ion batteries. So that's the goal, is to have this circular battery value chain. And I'll talk more about that when I talk about circularity and the trends there. But what's really driving the battery industry today is the Paris Climate Agreement, and how all these countries want to decrease their carbon emissions. And because of this, you could see by 2030, there's going to be a demand of around 5,000 gigawatt hours of energy, which you see today, this is 2025, so next year, but that's like, what, 3 times the amount? So this is a huge amount of demand. We're going to see a huge amount of growth further than what we have today. And it's pretty mind-blowing when we think about how our lifestyles, how we interact with technology, all of this are going to be changing very rapidly, especially with all the influx of funding. But there are a lot of challenges to this. There's volatility in the price of different materials that go into batteries. So you probably heard of all the layoffs from like Tesla recently, but our Next Energy. And a lot of these layoffs are happening because the price of lithium decreased so much, the economics of their business model shifted, right? So unfortunately, they have to cut costs and they choose to lay off the workforce. And then also there's tons of incentives from these taxes, from the tax incentives. Like, did you guys get an electric vehicle and get that tax incentives on your write-off? I got mine this year. So that's exciting, right? Us consumers get benefits. But below the surface, there's a huge crunch for talent right now. There's really, supply chains are another thing that's really volatile with geopolitical uncertainty. So lots going on in this industry, but let's focus on the smallest unit of this industry, right? The cell. And when I realized that batteries were like, oh, this is going to be the next thing, I want to learn more about battery technology and where do I want to focus in this industry? I decided, I want to innovate battery technology at the cell level. And I found a startup near my university called Innovate Corporation that focused on silicon anode technology. And so when I get into battery materials, I could talk more about that. But first I want to set the stage with what is a lithium-ion cell. So the difference between a battery and a cell, yes, there's differences. A cell is that single unit and a battery is a collection of cells. But there is a caveat where we have, say, in our smartphones, we maybe have one cell. So we could call it the phone battery. So that's the case where one cell is the battery, but you can never say that a battery pack is a cell. So to clarify, when I'm talking about cells, I'm talking about just the single unit. And there's primary cells versus secondary cells. Are you guys familiar with the differences between these? I see some nods. Cool. So primary cells are like AA batteries or cells where you just use it once and you dispose of it properly. Secondary cells are rechargeable, like the lithium-ion batteries in our devices. So lithium-ion cells are typically secondary batteries, and they come in a variety of formats. Now, if someone's asking me, hey Jill, what are different types of cells? Or can you point out this type of a cell? I would go, what do you mean by type? Do you mean format? Or do you mean the cell chemistry and materials inside of the cell? So type is a very vague term, but when we're talking about formats, we're talking about specific like coin cell format, cylindrical cell format, prismatic, or pouch cell format. And those are the four main types of cell formats that you'll see. So lithium-ion cells contain lithium. Pretty obvious, right? It's been the name. Lithium is a very small atom, which means that the reason it's used in lithium-ion batteries is you can pack it very densely. So you have that high energy density. If you use a bigger charge transfer carrier, it can often take up more space. You won't get that optimal high energy density. And they're also really special because they have only 3 electrons, which means they have 1 electron in the outer valence. And that's what participates in redox reactions or electrochemical reactions, giving away the electron, bringing in the electron, and that's how they convert electrical and chemical energy. So really special ion there, an atom. And I like to think about, how can we visualize how small a lithium ion or lithium atom is? So if you take the width of a human hair ratio to the ionic radius of lithium ion, it's the same as if you take the planet Earth radius as like the human hair, and the Space Needle in Seattle, the height of it is like the diameter of a lithium ion. Another comparison is if you think of, have you guys seen the Sphere in Las Vegas yet? I see some nods. So it's basically like if the Earth were the width of a human hair, then the sphere is like a lithium ion on the Earth. And I use the hair reference because in a battery, you'll see they're composite materials and they contain a lot of particles typically. And those particles, each single particle is about the width of a human hair. So very tiny, very tiny. And getting into what's inside of a lithium-ion cell with these composite materials, you'll see layers. And I love how in Shrek, we talked about how onions have layers and ogres have layers. Well, batteries have layers, though I don't think we talk about battery feelings very much. But you can see this is an optical image of a cross-section of the inside of a battery. Now, no matter what cell format you have, like a pouch cell on the left or a cylindrical cell on the right, they all have layers. And I'll get into, or the next slide actually, are what these layers are. So here's a representation of just a single layer. In a typical cell, you'll actually have multiples of these layers stacked. But just looking at a single layer, you have the electrodes, which participate in these redox reactions. Which I'm going to go, this is high level, but a bit technical at this point. So bear with me if this is a little bit too much for the moment. But the electrodes, or the anode and cathode, is where the lithium will participate in the redox reactions. The current collectors collect the electrons from the lithium that react and take them to the external circuit. The electrolyte is the liquid or solid that fills the entire cell. So you don't really see it in this image, but think of it as permeating throughout the whole cell there. And the separator divides the electrodes from each other because you don't want an electrical contact between those electrodes. That's a short circuit, that's a battery fire. We don't want that at all. So be safe, use your strong separator between it. And the separator, though, it allows the lithium to move back and forth between the electrodes. So we say it's ionically conductive, but not electrically conductive. And then finally, the tabs of the cell are typically welded to the current collectors, and you can see the pouch cell there, image at the bottom. The tabs are the two metal bits that stick out. And then the pouch or the container contains the cell, because we don't want the cell being exposed to air or moisture in the environment, because it'll destroy the performance of that cell. And also, unfortunately, there's toxic materials inside of those cells, so we don't want those getting out of the cells too. And just briefly, so redox reactions are what creates that chemical to electrical energy conversion and vice versa. And I like to think about, there's so much that happens inside of a cell at once during charging and discharging. The lithium is everywhere, and it's reacting with these particles that are in the anode and the cathode on both sides of the battery at the same time. And you have not just those wanted redox reactions where you can get the electrons or give the electrons. You also have unwanted chemical reactions, unfortunately, inside of your cell that you're trying to prevent from happening, because that's what can cause the degradation. You also have particles expanding and contracting when they take in and release lithium ions. So it's like this orchestra of moving parts where each particle is like an instrument playing a note to make a battery function. There's really a lot going on, and this just scrapes the surface of the complexities on the nanoscale of batteries. And just briefly, how they actually work. So when you charge a cell, you can think of it as the lithium moving across from one side to the other during charge and discharge. So when it's charging, the lithium's moving from the cathode to the anode, and when it's discharging, the lithium's moving from the anode back to the cathode. And the anode, so when a battery's fully charged, the anode stores all the lithium, the usable lithium for capacity. And then when the cell is discharged, the lithium will go into the cathode. But as it's moving, it's participating in a redox reaction on both the anode and cathode throughout that to create that conversion. So to summarize this, what is a lithium-ion cell? Because I often hear people will say, oh, there's lithium-ion cells and there's lithium iron phosphate cells. But actually, like lithium iron phosphate cells are a type of lithium ion cells. So there's multiple different types of lithium ion cells. The general themes are that they can store and convert energy through redox reactions. They're the lithium ions are the charge transfer carrier. So for like sodium ion batteries, sodium is the ion that's the charge transfer carrier. And then they also all have layers of materials. Are there any questions about lithium ion cells before I move on?
How fast does the reaction work?
How quick?
Yeah, like how fast are they moving across the membrane or whatever?
That's a good question. So when it comes, so the question was, how fast do lithium ions move through the cell, right? So I'll answer this more generally because I don't have the actual numbers of ion conductivity in front of me. But basically, the movement of lithium ions is really important because that determines the charge and discharge rate that's possible. And so you can change the speed of lithium ions through the battery if you change the charge and discharge rate. However, when you reach like the maximum charge rate or the maximum discharge rate, there's certain processes that dictate how fast that's going to be based on what's the slowest rate that the lithium can move through. Typically, the slowest that lithium moves through is due to the diffusion of lithium ions through the particles of the electrode or through the electrolyte itself, especially if it's like a solid state electrolyte material. So I like to think of as the lithium moves through the cell, it's like going through an obstacle course. And at different parts, whether through the separator or through the electrodes or wherever it may be, there's like a different obstacle it's going through and there's a different rate that it moves through. But actually the redox reaction is the quickest part. That's like electron fast, you know? So good question. Any other? Yeah?
I mean, I guess that answers the tangents and whatever. The question I wanted to ask is, in electric cars, you can have batteries with like a 20C discharge rate versus like a laptop battery could be like a 1C discharge rate. So it sounds like what you're describing is that the chemistry of those two cells is different, not necessarily the fabrication layer itself.
Yes. Yeah, so depending on the application, your cell design, the cell materials are going to be different. So for applications like your cell phone battery that require a lower current limit, like maximum current, you can use like rate limiting materials pretty well. Like oftentimes they'll use like a gel polymer electrolyte instead of liquid, but there's benefits to that. But then for like electric vehicle, that's the race, right? To see how can we get the fastest material, you know, into the battery or the fastest transporting. Anyway, yeah. Great questions. All right, I'll move on to battery technology trends. So I'll talk a little bit about the latest of what's going on, which you guys were talking about a bit about the rates, right? At the cell level and what are the trends there. Then we'll go into the pack level, gigafactories, and circularity for batteries. So these are like the way that the industry's trending right now. This is all how cells are being designed to perform better. So they want higher energy density cells. Like you'll see the pickup trucks today, there's like complaints if they tow anything that the range is severely cut. So by having a higher energy density, they'll be able to tow and still keep their range. Also longer cycle life. We don't want a battery in our car to last just 10 years, like could it last 20 years, 30 years, you know. Faster charge discharge rate, wider temperature range. You guys notice all the news about the car batteries aren't able to be charged in the wintertime. That's a problem for battery cell chemistry level. And then also safer. They want to make them less toxic with more abundant materials and lower cost. So I'm not going to dive super into the different materials, though I am a material scientist and I love to talk about crystalline structures. Does anyone want to hear about crystalline structures? Okay. I see shaken no, but hand up. Okay, interesting. I'll just do this briefly. So cathodes, I like to divide them in three categories, 1D, 2D, 3D. This doesn't have to do with actual spatial dimensions. They're all actually 3D crystalline structures, but I'm talking about the way that lithium moves into these structures. So one-dimensional cathodes or olivine cathodes are materials like lithium iron phosphate. Have you all heard of lithium iron phosphate? It's now being used in like Teslas and other electric vehicles around the world. These 1D cathodes, the way that lithium moves through them is like moving through a tunnel. So it doesn't have a lot of wiggle room as it goes into the structure, and that limits their charge rate. So that's why you're not going to get maybe I don't know, maybe you can engineer a fast charge LFP battery, but remains to be seen. But it's made of more abundant materials, they're lower cost, they have a longer cycle life than other chemistries. So there are tons of advantages to these materials. Getting into 2D cathodes, layered oxide cathodes, these are your nickel-based cathode materials. So you have NCM, NCA, and the numbers next to the NCM, so this is nickel, cobalt, manganese. And the first number corresponds, it's like the ratio between the three materials. So like 111 are equal parts nickel, cobalt, manganese, but you have like 532 is 50% nickel, 30% cobalt, 2% manganese. And the higher nickel content you go, the more energy dense of a material you get. However, you get a poor cycle life. So it degrades quicker over time. So there's always trade-offs with these materials. You can't get that high energy density, amazing cycle life, amazing temperature range. It just, unfortunately, our materials aren't quite like that. But these materials are very common in our electric vehicles. LCO, lithium cobaltite, is often used in cell phone batteries. They're great. They work well, and it's 2D because lithium will move in like planes. So you see the green dots are lithium in that diagram. For spinel cathodes, these are 3D cathodes, and these are the fastest rate capable ones because the lithium can move into these materials in 3 directions. However, they have a lower cycle life and lower energy density. These are like lithium manganese oxide materials. And moving on to anodes. So I could talk for days about anodes because I did anode research, so I'll try to limit myself a little bit. But anodes are the negative electrode in a battery. Graphite is the most common one that's used in so many devices. And it's a great electrode. Like, it is amazing. It's low cost, it's mechanically stable, it's low voltage, it has great energy capacity, though we could argue that it could be more energy dense, and that's a limiting thing. It has long cycle life, right? And the goal would be to have a wider temperature range with it, though, and a better charge and discharge rate. But it's really good. Like, it's good enough for our batteries these days. And good enough is a battery pun, though he worked on the cathodes, if you know who I'm talking about. He got a Nobel Prize. So when I was a researcher researching silicon anodes, which I'll talk about in a second, it's really hard to improve upon this technology, and that's where we're kind of at in the industry. Another anode material that I used to think was super boring because it was a higher voltage anode material, and it's also like really low energy density, like it doesn't hold a lot of jam-packed lithium, is lithium titanate. But when I found out that these anodes can do like 30 C cycle rate, like super fast, and they're super stable, and they're amazing across a really wide voltage range, and they can cycle for not just thousands of cycles, but tens of thousands of cycles. Amazing, amazing. And I just talked to somebody who, one of the really tough experiments in batteries is to do 3 electrode cell experiments. And he said that using lithium titanate as a reference electrode is sometimes more beneficial than lithium metal because it's so stable. That just blew my mind, but that makes complete sense. So lithium titanate is an awesome material, but it does have low voltage and low energy density. It's usually used in like stationary storage applications, not so much in electric vehicles. Silicon anodes are considered like a next-gen battery material. These, you can see the energy density here, are an order of magnitude higher than graphite. Crazy capacity, crazy energy density for this. And there's so many advantages. Like, it's also low cost, it's also low voltage, it's abundant. And what's interesting about silicon is, instead of, like, you've seen all these materials, the lithium like inserts itself into the structure, the crystal structure. Silicon actually alloys with lithium, and it turns the crystalline silicon amorphous. It's no longer crystalline. Really interesting process. But the challenge with silicon, though, is that when you do have the lithium going to the structure, it expands a lot. And if you have a battery in a package, if it's expanding a lot, then it could just cause problems. It could like swell too much and burst the container. So you have to really, when you design a silicon battery, you have to make sure that your packaging is going to keep it intact. Also, when it comes to the expansion and contraction of the particles, it can cause cracking, and the particles can actually break off and isolate themselves, they call it, so that they can't participate in the redox reactions. And it also can form a thick, what's called a SEI layer, or solid electrolyte interphase layer. And this is a coating of the electrolyte decomposition on the surface. But there are a lot of misconceptions about silicon, and coming from the silicon world and thinking about how people think about graphite, I find a lot of scientists take a lot of assumptions about graphite and apply it to silicon. And so when you're doing research on different battery materials, it's important to not come with a lot of assumptions about it when you're researching. And I think we just need to manufacture silicon anodes in a way that's better for their performance, and that'll help make sure that we can introduce this technology and commercialize it, which the company I used to work for, Innovate, just came out with an electric motorcycle partnership. So there's actually a motorcycle, the Lightning, that uses a silicon anode battery technology. That's pretty amazing that we're there. And finally, the last anode material I'll talk about is lithium metal. Now, lithium metal is the holy grail of anode materials because it's the highest energy dense anode, but it's also probably the most difficult to work with because it reacts to air and moisture. It can catch on fire in air. So if you picture, if you're manufacturing this on a big factory, do you know how expensive a dry room is to keep dry for long periods of time, or to keep it in an inert gas? So it's really expensive to manufacture. And also a challenge is, this drawing here shows the formation of dendrites, which are like spikes. So as you cycle the battery and the lithium's going back and forth between the anode and cathode, picture it like a traffic jam. If the lithium can't react with the surface or form on that surface of the lithium metal, it can start building these spikes that can come out, puncture through the separator, which would then create a short circuit across the electrodes. That's when you get heat generation, thermal runaway, fires, and all of that. So a lot of research right now is going into different kinds of passivation materials on the surface of lithium metal anodes and other techniques to try to prevent dendrite formation, which leads me to solid state batteries. So this is something that I think has been pretty hyped up. I don't know, would you guys agree it's hype? I see nods. Hype, cool. A lot of like minds in this room. So yeah, solid state metal batteries are, if lithium metal is the holy grail of anodes, solid state batteries are the holy grail of lithium ion cells. So the goal with the solid state batteries is to make batteries as energy dense as possible. So you're using lithium metal anodes, and then the materials are super compact. You have high energy density. And there's 3 types of solid electrolytes that are used in solid state batteries: polymer, sulfide, and oxide types. And there's a lot of different ones in those 3 categories. So there's not just 3, there's endless amounts. But these are often really difficult to manufacture, and there's a lot of research going on. But there are a lot of solid state battery companies that have produced prototypes that are now partnering with gigafactories and with OEMs, auto companies. You might have heard, like, QuantumScape is a big one that's been in the news, has partnered with PowerCo or VW to maybe try to make a manufacturing plant. So we may see this, though, I would say in maybe 10 years, maybe more than that. So lots of challenges in that space. And I'll pause there with the cell technology and trends. Does anyone have any questions about any cell trends you may have heard of? Yeah.
Like in terms of the different materials, chemistries, anode materials, what is the limiter in terms of battery performance? Or what is the slowest, most important limiter in modern battery design?
Yeah, so the question was, what's the barrier to performance in battery design? Like, is it the anode? Is it the cathode? Is it the electrolyte? Is that what you're asking? Yeah, that's a really good question. And it really depends on the cell chemistry and the type they're using for what's the limiting factor of that. I would say, though, that typically the cycle life performance of batteries is cathode limited. So like if it uses graphite, the anode's usually fine for the life, but over the time the battery is in operation, the cathode will degrade more. But it's like a snowball effect, a ripple effect. So as the cathode degrades, the reaction products, the chemicals that degrade in the electrolyte go over and affect the anode, which then degrades, which affects the cathode, and the electrolyte further degrades. So it all exacerbates each other. And as a battery scientist, identifying when I have a certain cell chemistry, what's the limiting factor, and trying to solve that issue is like one strategy to try to improve the performance, but it's really tough to tell sometimes. I do see mistakes being made though, when somebody will make an assumption of like, oh, we just need to improve the conductivity of the electrode, and let's throw in some additives and improve the conductivity and it'll solve all our problems. But it's like, was the conductivity the problem to begin with? And techniques to understand what's the limiting factor can be really complex. Like I was talking about the 3-electrode cell experiment using reference electrode. It's a really tough thing to do and reproduce. And yeah, good question. Yeah.
How efficient is the recycling of these batteries? Is that something that they're working on big time, or is it, where are we at today with recycling of these lithium-ion batteries?
So recycling is definitely something that will be there in maybe the next decade, but I think the misconception is that we'll be recycling battery cells now. I mean, we do recycle them now, but right now, most of the recycling horsepower in the US has to do with gigafactory scrap. So a lot of the cell recyclers are focused on partnering with cell production plants and recycling their scrap, but they're prepping for the volume of electric vehicle batteries that'll be coming off the vehicles in the next 5-10 years or so. So we'll see that kind of the peak shift to electric vehicle batteries being the primary driver of recycling. But yes, I'm pretty sure recovery is over 90% for battery materials, but they mainly focus on like the more expensive ingredients, right? So they don't really care about the polymers inside of the batteries. It's more the nickel, the cobalt, the lithium, copper, foil. Those kinds of materials are more recoverable. Yeah.
I have a question from the internet. They ask, what is your opinion on non-lithium cells like sodium-ion? Theoretical density too low to compete with lithium? Promising? Some other problem?
Yeah, the question was about sodium-ion batteries and if they can compete with lithium for energy density. And what I'll say is there's a place in the market for, I think, any type of cell, because there's so many use cases for them. So sodium ion is great when you don't need as large of a energy density, perhaps, like stationary storage. But we're actually seeing sodium ion kind of meet on par with like lithium iron phosphate energy density, which there are now vehicle batteries that are being made with sodium ion batteries. So it's pretty exciting that, yes, their performance is on par with lithium ion. It's maybe the supply chain isn't as robust, like it's a newer technology for manufacturing, but just like with lithium, I'm sure with some research and some, good engineering, we can get it there. So it's definitely a great battery technology. I saw another question.
No.
Oh, okay.
So what's the difference between I've seen some primary lithium cells and secondary lithium cells?
Yeah.
As far as chemistry and composition, and then why does it seem like there's only one manufacturer making larger primary lithium cells?
I don't know the answer to that. Yeah. Does anyone else know? Yeah.
I think the lithium primary cells are mostly hearing aid batteries and stuff like that.
Well,
like
but
really
they have
small form factor.
Energizer makes AA's, AAA's, 9 volts, but they seem to be the only ones.
They
at
must be
least
more
here.
expensive than alkalines, though, right?
Oh yeah, they're
Yeah.
way more expensive, but I don't know why.
Yeah.
Right.
Well,
Interesting.
I mean, they clearly have a market for it, so why doesn't anybody else get into that?
Maybe they'll hear this and think of the idea and start a primary cell company. Yeah.
Maybe I should have asked this at the beginning, but in like a cell phone battery, is there like juice in there? I thought these things were kind of like basically solid.
You know, I think it's like semi-solid. Like there's some liquid, but it's like some of them are more like polymer based or gel based. So
And they're still not considered solid state? Because I actually thought, like solid state would be mixed in with,
so yeah. Sorry, I'm getting held up because there's a lot of like, oh yeah, you wanna
Only 'cause
answer?
I have to research.
Yeah.
I opened some up. It's not like you're gonna wring it out with a sponge, but there's a little solvent. You're gonna like whip it, like so. There's still
Yeah.
solvent in there, but it's not like wet.
Yeah, I think when it comes to solid state batteries and the announcements for them, like, oh, solid state batteries are used in cars. When you dig deeper, you find out it's like semi-solid state. And solid state, like all solid state batteries, will say all solid state batteries. That's usually how you can find the differentiator. So those are typically used in like pacemakers and things like medical devices, things that it's okay to spend a little bit more on manufacturing, and they're like super niche use cases. But so yeah, a lot of it's semi-solid right now. Good questions. Love it. All right. Pack level trends. So after I've a few years at doing cell level research, I started thinking, well, like I'm tired. Like cells need to be safe for sure, but like the pack is the thing that really makes the cell safe and like coddles the cell, right? Protects it from the elements. So we need safe packs. And my next role was in consulting, doing pack level validation testing and abuse testing. So it was a lot of fun. I would say my job was torturing batteries at that phase. And so pack level trends, the goal is to design that battery pack that can optimize your cell performance while being as safe as possible. And I put an asterisk for the warranty period because, with engineering, you can engineer a really safe battery, but the forces of the universe, like corrosion, are going to happen eventually. So, we want to make sure that we're designing batteries that are safe for the duration that we expect them to be in use. And that's really important. And battery packs, the major areas that I want to highlight for the trends right now are the thermal management. There's a lot of different types of techniques, active and passive thermal management of the cells. You want to maintain them all at the right temperature, the same temperature, so that they all degrade at the same rate. Can you imagine after years if there's this thermal imbalance? Some of them are super cold, some of them are super hot. That means they're completely like different states of health. And it's going to be harder to manage those cells. Corrosion mitigation is a big one, especially the higher voltage you go, the more you get an effect called electromigration that can happen where the atoms in the wires where you're applying a DC current over a long time will actually move, causing pitting. And then if you have moisture that comes into the pack, it'll like accumulate in those pits and cause corrosion, which can like cause a battery outside of your battery, which is essentially a short circuit. Short circuit, you get thermal runaway and fires. So making sure that you're protecting the battery from moisture, making sure that you're using a battery management system to monitor and control your battery. So the battery management system does a lot of different things. It monitors the voltage and the current and the temperature of your cells, and it manages if there's any faults, if there's anything that goes wrong in your battery, it hopefully detects that and manages that in a safe way. And there's a lot of cool tech coming out around like smart battery management systems. So a lot of them for those of you who are electrical engineers, you'll like this. A lot of them will just, it detects the data, but it doesn't store the data. But imagine if it could store your battery data over the lifespan of your vehicle. If it could store the data, then that's so much battery data that you could use to inform like cell performance and what's going on during the life cycle. If a driver drives super fast and whatever, how does that affect the battery performance? And then taking that data, you can design a better battery, right? So having a battery management system that can not just detect, but like capture that data, update it, upload it to the cloud, run an API so we can all play with that data, like that would be a lot of fun to have. But also there's a big challenge when it comes to recycling or second life use. If you get an electric vehicle battery, you don't know how the driver treated the battery. You don't know what kind of life this battery had, if it was coddled or if it was just, thrown against the wall. So having a smart system that can tell you what the health is of that battery when you receive it for recycling or whatnot can help with that deciding of how to dispose of it properly or how to recycle it. And just a little bit on the effects of temperature. So like I mentioned earlier, in the wintertime, there were lines and lines at these charging stations because it was taking forever to charge a battery. And while I could see how someone would get really upset, like, oh, I paid for this car. It said it was going to charge at this rate for fast charge. Why isn't it doing that? Well, we talked about lithium plating and dendrite formation. So if the battery's really cold, the lithium moves slower through the materials, and it could cause a traffic jam and could cause lithium plating if you charge it too fast. And so those slow charges are actually protecting a lot of people from any kind of harm and danger. But it is a challenge to maintain that temperature so that you can have safe charging and safe operation and keep that temperature uniform. And then the risk of lithium plating. So I love this diagram and this picture here. This is with a graphite anode. And what this is showing is different charging rates. You see like C/50 on the far left and then 3C on the far right. But you notice the color of the electrode is different across that. The darker ones, that shows no lithium plating, but when you see that gray color on the right, that's an electrode that has lithium plating that has happened to it. So when you take apart a battery, you can visibly see this plating sometimes, and that's why the lower rates are often safer for a cell. So a little bit about pack trends. Any questions about packs, battery packs? Cool. Okay, we'll go on to gigafactories, and then I'll go through this kind of quickly. But you've probably heard that they're building a lot of gigafactories in North America. A lot of challenges with this. I've been working with some gigafactory clients in my current role. So after my pack design, testing, torturing battery career, went into consulting, where I now work as the lead of battery consulting for Accenture in North America. And so some of my clients are gigafactories, and it's really interesting to see the different challenges they're facing with equipment selection, costs being really high, labor shortages, finding out where to even put a gigafactory, like where should I build this? Because there's different taxes and tariffs in different regions. So it's a lot of challenges to get these up and running. Luckily, we have like the Inflation Reduction Act and the IIJA pumping billions of dollars into this industry. And I was going to ask, I just showed that, but how many gigafactories do you think are in the US today? About 20? You guys might have already seen the slide. I ruined that. Any other guesses? Maybe you saw it. No?
Prior to the slide one.
One? So this one has about 32, but I think there's even more that I don't see on here that I know that are going up. So and maybe they're announced in the past month because this is a month old. So there's a lot coming online. And what a lot of these companies are doing, like the established OEMs who don't have a experience in cell manufacturing, is they're partnering with an Asian cell manufacturer who's been doing it for many years, like CATL or SK is from Korea, LG Chem is from Korea. And so we're seeing a lot of different gigafactories being constructed and starting to operate. And I do have a video. I'm going to plug my YouTube channel. So I have a video on how a battery is made. it's actually made a lot like how cakes are baked. So I bake a battery. It's edible, and you can make I have the recipe that you can actually make it at home. And I'll talk through the steps though of making a battery, just using the cake analogy for this. So if we center ourselves on what a battery is made out of, the layers of materials, right? And it's packaged into a different format. How does it get there? How do we get from the raw powders to this material? Well, you just bake the cake. You mix all the powders into a batter using a solvent. And you could use a variety of different mixers, from a small scale on the left to a gigafactory scale on the right. After you mix it, you coat it. It's kind of like pouring it into a pan. You coat it on a current collector typically. So that's a picture of a coating machine with a cathode on an aluminum current collector. And these can also be on the small scale, so you can coat it by hand if you want. But typically for a gigafactory production, you want to use an industrial coater that also has an oven attached to it. So after you coat it, after you pour it in a pan, you put it in an oven and you bake it. And it takes all the liquids out and makes it into that solid film, just like a cake, right? And then you calendar it. So I guess you don't do this part for a cake. You don't take a rolling pin and just flatten it out after you bake a cake. You maybe do that with your pizza dough, but not with a cake. So calendaring is when you press it between these metal rollers that can be heated, kind of like that. Again, there's different scales of this, and that's to compress it and make it as energy dense as possible. After that, you have your cake, but then you want to make a multi-layer cake. You got to stack it up, stack and assemble all the pieces. And then this is where the formatting takes place. So if you have a cylindrical cell, you wind it into a cylinder. If you have a pouch cell, you can stack it using like a Z-fold sometimes, or you can even, for a prismatic cell, you can wind it and then smush it into a prismatic container, rectangle container. And then finally you pour in the electrolyte, which you don't do to your cake, I guess at that point. You don't. In my video, I made like an electrolyte, like it looked like Gatorade or something. And then I was like, should I pour it in my cake? And I decided not to, because I wouldn't have been able to eat it if it was like soupy, but that's what happens. You pour the electrolyte in, you fill it. And then after that, you have your cell contained in its case, and you do what's called cell formation, where this could be a series of aging the cell in high temperature. You just store it for a while, or you could run through a couple cycles, charge-discharge cycles. But the challenge here is, picture you make a battery, and make 100 batteries, and like 50 of them have problems. Like you do an OCV test and there's a challenge, and you're like, well, what went wrong, right? You had this whole manufacturing process, and you're like, which step did I go wrong at? And that's a problem that a lot of factories are running into, where they don't have the visibility over the data across their production process. So it's really important when these gigafactories are designed that they are built to understand the different processes. So like one example of where I worked, one day we got batteries that were performing really bad and we didn't know why. And we had to comb through all this data from the process, not knowing where the error was. And we found out that the supplier kind of gave us a different material than we thought. But it took months to figure that out. So when it comes to production, if you're gigascale production, if you have months of downtime, that could tank your entire operation. So the data picture when it comes to gigafactories is really important, really interesting to me. I love data. So, and any questions about cell manufacturing? Yeah?
What's the yield rate for like one of these factories? Again, like how many cells do they really make? Like 90% are good, or like?
So it can really vary. What I hear is that a typical like scrap rate would be 30%, so yield rate 70%. CATL, which is the biggest battery manufacturer in the world based in China, they say that their quality for battery output is 1 parts per billion, which is extremely high. And I think they have the best technology there to do this kind of digital monitoring of the equipment and everything. But scrap rate could even be up to like 70% sometimes. Like it could be really bad if you don't design and plan right, which is why people should hire me and my team to help them build their gigafactories and do the right due diligence for equipment and all of that.
Question from the internet. What are your thoughts regarding use in the human body? Yeah, I have to infer a lot.
Cyborgs.
Yeah.
What do I think about cyborgs powered by batteries? No, I'm sure it's for medical devices, right? So, yeah, I just, there's so much testing and validation that goes into batteries, especially when they're being used in medical devices. And so I think as long as they're doing the right kinds of safety tests, you should be fine. Should be fine.
Definitely seen some people implant just your normal lithium-ion spark bun pouch cell into them. Any thoughts on that?
Don't do that. Don't implant a pouch cell into yourself, please. If that leaks, if your body corrodes that package and causes a leak, you could have hydrofluoric acid go into your guts and that will kill you. So don't do that. The battery I make in that video is not a functional battery, but you can eat it. So if you must ingest a battery, bake that cake.
You get a charge out of it?
All right.
Another one? Yeah. Prefacing with maybe too in depth, but can you touch on SOC estimation and battery modeling techniques? Linear delay obviously doesn't cut it for lithium, so how do you handle estimating how much energy you have available? I guess.
I'll ask that person to email me their question because I think that's a longer explanation than I can give here. So, yeah. Thank you, though. Yeah. Got some highly technical callers calling in. I love it. All right. I'm almost out of time. Just talking about bringing it all together. So after we manufacture it, after the battery's been used in its full life, circularity, which I loved your question about recycling because that is front of mind, right? How are we going to create this sustainable battery value chain and closing that loop in the value chain is recycling. So a lot of the funding coming in is motivated by the Paris Climate Agreement. And this is something that's leading to the formation of what's called the battery passport. So we talked a bit about data from the battery management system throughout the battery's life in a vehicle. And we talked about data from a cell production plant, right? So a battery passport isn't necessarily what it sounds like because you're like, why does a battery need a passport? It's not going to like travel anywhere, you know. But a battery passport stores all the information for the cell of the battery. It's basically a digital twin of the battery cell. And so all the data around the battery goes into that passport and it's stored in a data lake, but it's accessible to certain people who need access to that data. And this is something that the Global Battery Alliance is working towards, and Europe has actually mandated this through the EU Battery Directive. So this is in progress right now to create this system. But you can imagine it's really challenging to put battery data all in one centralized database, especially when companies are so concerned with data privacy. So understanding how they're going to do that is a big challenge. And that's why they're doing these different concept stages towards this battery passport. But it will consist of a global reporting framework to govern the rules and auditing, reporting for ESG parameters related to batteries, also a digital ID for the battery cell, and harmonizing of all digital systems across the value chain for the battery. It contains a digital platform, so different authorized stakeholders can access that data. So if a battery recycler gets a battery, they're like, it has a barcode, but what is this? It can scan it and have access to what's inside of it so it knows which recycling stream to put it in, because you don't want to mix up the battery recycling streams. That could destroy your recycling operation and contaminate things. And also it's a quality seal for batteries. So making sure that we have batteries that are vetted, that are safe to use. I see a lot of issues with batteries that aren't necessarily high quality being sold on the market, there's a lot of risk in that for consumers. And so we want to make sure that consumers are safe. And by doing this, we hope that Battery Passport will enable transparency across the battery value chain. It'll create a framework for benchmarking batteries. And we could also validate and track the progress that the industry is making so that we are creating a sustainable industry itself. That's one of the issues with a lot of industries is we're not even gathering data around the different processes, and we don't know what we're leaking into the environment, right? So this is all to make sure that we're setting up this industry to reach those carbon goals, and data and this Battery Passport are central to that mission. I won't really talk about second life batteries, but that's a goal. Like a lot of battery packs are designed for barely even first life, let alone second life, but we hope one day that we can design batteries to be used in multiple different applications. And that's one way to extend the life and reduce waste. And then we already kind of talked about batteries through the question, which was great. I won't say too much more than there's different processes for recycling. And some of these actually are fueled by like natural gas or generate large amounts of sulfuric acid waste. So we need to also find recycling methods that are more environmentally friendly that we can power using electricity and renewable sources of energy. So lots of challenges with recycling there. So that is all, y'all. So I do have a special gift for you all. I don't know, bonus if you want to learn more. So if you follow that QR code, it links you to my link tree, which there you can find my different resources. But I check out the battery industry onboarding resource. It's a series of emails with links to different resources about the battery industry. So like YouTube videos, news sources, even for those of you who like to play with like Python and battery data, I include databases where you can find open access to battery data there. And yeah, there's just a lot of resources that are sent out. So if you're interested in working in the industry, learning more, that's a good place to start. So yeah, I'm happy to take any more questions.
I think you've answered most of them.
Cool.
We don't have any online questions from anyone.
Cool.
You suggested you were saying there were pure silicon anodes in that motorcycle battery? Or was it a mixed graphite and silicon still?
So they're silicon dominant.
So more than 50%?
Yep.
Oh, wow. I thought the industry was still 10, 15.
Yeah. So they're, I'm trying to remember what the article claims because I know what it is. So it is more than 50% silicon though. Yeah. Yeah.
So I noticed the locations for the gigafactories that were existing in the plan. There's one in Texas, maybe like three in California, not that many on the East Coast. There was a line, clustered line in the Midwest, almost down Florida. It doesn't seem to match any population density here. So why are those states?
Yeah.
Low labor, maybe?
Yeah. there's a kind of a-
Yeah. So the question is, why are these battery gigafactories being built in like these clustered locations? And what were you saying? The labor?
Labor cost or subsidies from the governments.
Yeah, labor cost, availability of labor too. So and then the land cost, energy cost is a factor. And, you know, a lot of them are being clustered around Michigan, Ohio, and there we have a lot of automotive industry. So you have a lot of skilled workers in different fields. You have low cost of land, all of that. And then in the South, there's also a lot of automotive industry and aerospace industry. And so that's why a lot of them are clustered in the Southeast there. And then out in California, I think those are, you know, Tesla mainly. And that's an interesting choice, I think, with the high cost of land in California. But Reno, Nevada, you know, that's a lot of land and closer to their plant there. So, yeah.
Are there good sources of like, supply for cells and packs? Like necessarily UTT, but just suppliers that actually sort of specialize in providing batteries at a not high price.
Yes.
Decent battery.
So the question is where can you purchase batteries and cells for a decent price? I mean, my perspective is getting it for like an automotive company. So that's like a high volume amount. Are you thinking more of like a hobbyist level? So a lot of my hacker friends get them from like eBay and other things like that. Of course, they also know how to do their due diligence to make sure that they're safe. So find a trusted friend. What?
Or they actually function.
Yeah. Yeah.
There's endless debate about how lithium cells should be treated in order to optimize their lifetime. Is there a good, I won't make you go into it, but a good resource you can go to for some actual factual data behind it rather than guessing in wives' tales?
So yeah, that's really tough because so the question is how can you pamper your battery? Like how can you make sure you're extending its performance? And even as someone who was trying to maximize the performance of one select cell chemistry, it's tough to test for so many different variables to see how you can do that. So that's why I think you get like rules of thumb for like a cell phone battery. So for, like you've probably heard, don't charge it to 100% and leave it fully charged. That's because it exacerbates the cathode degradation at the high voltage for nickel-based. But if you have a lithium iron phosphate-based cell, that's actually okay to keep it a higher voltage. You probably actually don't want to discharge it too much. So like that's completely opposite, right? Depending on what the chemistry of the cell is. But for the most part, no matter what you have, it's good rule of thumb just to swing it between like 10 and 80%. And also keep it at room temperature as much as possible. Not too hot, not too cold. Yeah.
Question for interwebs again, and I am going to paraphrase this a little bit.
I've heard, so per charge, I'm not going to do that math on the spot, but what I've heard is that for like a battery pack from a car, it could be like a terabyte of data per, like, I don't know if it's a minute or like a per second, per minute maybe? I see a nod. Terabyte per minute. Does that sound about right? Oh. But it's a lot.
That's way more than I would have thought.
Yeah.
For such what seems like a simple process.
But a pack contains, thousands of cells. So, but still, it's quite a bit. And it also, like, it's a question of maybe you don't need, like how often do you need to sample that data point? For some data, you can maybe sample it once a minute, once an hour. Some of it you may want finer tuned. So how much data you're getting from the battery could really depend on like the use case you have and what you want to monitor and what data you want. And I've heard problems with like the bus bars of batteries can't handle a certain data load. And so the OEM will be like, well, prioritize what data we need. And we're only going to monitor these certain things. So it's a hardware, software, data threshold balancing problem. Yeah. And that was an online question. I was like telling you, you're answering your question.
It's totally fine.
Yeah.
Pure satisfied.
Yeah. What do you guys think? You're all going to become battery scientists now? Ready, set, go. Thank you.
And I just want to point out that PowerPoint is phenomenal online. I really apologize for
It's,
what's
it,
going on here. If anybody wants to scan the QR code, we can
The QR code worked for me.
on the screen.
Yeah.
Oh, look at you. Here, we can
I put it there
throw this
for you, bro.
around if anybody.